Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear, and this is another problem I posted recently on the Facebook group Daily Math Problems. This one involves an elliptic curve over a finite field. Anyway, let's begin. So first I have to tell you what the problem says. Um, so we're considering an elliptic curve given by the equation y squared equals x cubed plus x plus 1. This is what's known as an elliptic curve in Weierstrass normal form. I'll get into that a little bit later. Anyway, there's a picture of this elliptic curve on the bottom of this page. This is the picture of what the elliptic curve looks like over R, over the real number field of real numbers. But for this problem, we're only considering it over a finite field, Z5. That's just the integers modulo 5. It turns out that you can define an elliptic curve over any field you want. So you can define over reals, over complex numbers, over finite fields, or over rational numbers. But in this case, we're considering over Z5, which is a field. Okay, so there's two parts to this problem. In part A, I'm asking you to compute the order of this elliptic curve over Z5, which I'm calling E5. And then for part B, this is the harder part. I'm asking you to show that the point P equals 0, comma 1, which I think you can see lies on E, because when y is 0, x is equal to 1, you can see that satisfies the equation of E. So, but now I want you to show more. I want you to show that this point P generates the whole elliptic curve E5. And what that means is that E5 is a cyclic group. It turns out that every elliptic curve has a group structure to it. And I'm going to talk about that later. And I want you to show that this point P generates this group. In other words, it's a cyclic group. And you can get all the points on E5 as multiples of P. So anyway, so that's what the problem says. And so part A, I think that's the easier part. Let's do that first. Um, we just want to evaluate all the points on E5. And that's pretty straightforward. I mean, all you really have to do here is make a little table. You just let x vary over all the possible values it can have over E5, which are just 0, 1, 2, 3, and 4, because there's only 5 elements of E5, of Z5. And then you just see what y has to be for those values of x. So when x is 0, I think you can see that x cubed plus x plus 1, which I'm calling f of x here, that's equal to 1. And you have to take it mod 5, but 1 mod 5 is 1. So we see that y squared has to be 1. That means that y is plus or minus 1. I prefer to write as 1 or 4 because I'm thinking of the numbers 0 through 4. But it's equivalent to minus 1 modulo 5. And then when x is 1, I think you can see that f of x is 3, because we're getting 1 plus 1 plus 1, that's 3. Well, 3 is not a square modulo 5, so that means that there's no value of y such that y squared is equal to f of x mod 5. That means there's no solutions. There's no points on this elliptic curve E5 when x equals 1. What about x equals 2? Well, when x equals 2, we're going to get what? 2 squared. F of 2 is 2 squared plus 2 plus 1. That's 8 plus 2 plus 1. That's 11. 11 modulo 5 is 1. So again, y squared is 1. That means y can be either 1 or 4. And similarly, when x is 3, you're going to get 3 cubed plus 3 plus 1. That's 31, which is again congruent to 1 modulo 5. So you're going to get the solutions 1 and 4 for y again. Finally, when x equals 4, it turns out f of x is going to be congruent to 4. You get 64 plus 4 plus 1. That's 69, which is congruent to 4 modulo 5. And so that means y squared is equal to 4 mod 5, and there's two solutions to that, plus or minus 2, or if you like, 2 or 3. mod 5. So these are the points. And I think you can see there's a total of 8 of these points that we just found. But there's one more. These are finite points. And there's one more fact about elliptic curves. Every elliptic curve has another point, known as the point at infinity. So the way to think about that, I think you can kind of think about it graphically. Um, let's just go back to the graph of the elliptic curve. Um, if you can continue this curve, it's an open curve, which means it goes to infinity. And so you get a point in it. They call that in projective geometry. They call that a point at infinity. An open curve contains a point at infinity if it's open. If it's closed like a circle, it doesn't have any points at infinity. I hope that doesn't confuse you, but it's true. And so every elliptic curve has a point at infinity, and that turns out to be the additive identity element of the group associated with the elliptic curve. So we're going to get a ninth point, namely the point at infinity, which is also the identity element of the group corresponding to our elliptic curve E5. That means that E5 has order 9. And I've listed all the points on the bottom of the slide. Might as well read them off. We get the point infinity, which we usually write as big O. I guess you're supposed to sort of think of that as 0 because it's 0 if you think of this thing as a group. And then you get the points 0, 1, 0, 4, 2, 1, 2, 4, 3, 1, 3, 4, 4, 2, and 4, 3. That's 9 points. So that's a solution of part A. And then what about part B? Um, part B is a lot harder because you have to know how to add. You have to know the group law for elliptic curves. And if you guys don't know that, I mean, let me just give you a little tutorial on this. So I explained this on this slide, but they say a picture's worth 1,000 words. So here's a nice picture. So we have to know three kind of things of what to do with elliptic curves. We have to know how to add 2 points on an elliptic curve. And I think they call these 2 points P and Q. And it turns out that whenever you have two distinct points on any elliptic curve, and you connect those with a line, if you extend that line, you always get a third point. And here they call it R. And R turns out to be the negative of the sum. So, and now to negate, they don't show this on the slide, but to negate a point on elliptic curve, you have to draw a vertical line. So you'll get the point minus R, which is just the reflection of R about the x-axis, which they don't show in this picture, but I think they do show the point that P plus Q is minus R. It's just the point you would get if you reflected R about the x-axis. That's how you add 2 points on an elliptic curve. But you have to know a little bit more. You have to know how to negate. I already showed you how to negate. That's easy. So if x comma y is a given point P on the elliptic curve, then minus P is the point x comma minus y. That's pretty easy. But the third thing you have to know is what if P and Q are the same point? In other words, how do you double a point on an elliptic curve? Well, I think you can kind of see what's going to happen if you let P and Q approach each other. If P and Q are equal, this line is going to turn into the tangent line. So it's almost like what you do when you're adding two distinct points. The only difference is instead of taking a line connecting P and Q, you take the tangent line of P on the elliptic curve, and that tangent line always intersects the elliptic curve at a second point. So it's just the coordinates of that second point. And it's pretty easy to work out the algebra. I mean, that's the geometry of how to do group, how to do the group operations on an elliptic curve. But you can translate that pretty easily into algebra, and you can get formulas. And I don't even know if I have to go over these formulas, but you can get formulas for calculating the coordinates of P plus Q, as well as 2P And minus p is easy. If p is x comma y, then minus p is x comma minus y. And this is pretty technical, but you can just apply these formulas to calculate everything we need to know. And if you do that, if you start with p, you can use the group law to calculate every multiple of p. Um, and it turns out you get every point on the elliptic curve as a multiple of p. That's what we wanted to show for part B, that P generates the elliptic curve E5. And I've showed it here by calculating these points. Maybe I should motivate this a little bit. So P is a point 0, comma 1. We're given that. How do we know 2P is 4, 2? Remember what I said about 2p? If you double a point on an elliptic curve, you're taking the tangent line, you're taking the second point um, on the tangent line. And let's just go back to this formula for the slope of the tangent line. Remember the formula for the elliptic curve is y squared equals x. In our case, it's x cubed plus x plus 1. So if you take the derivative of both sides of that equation, you get 2y prime equals 3x squared plus 1. So you get y prime equals 2x squared plus 1 over 3y, or 3x squared plus 1 over 2y. We already know x and y, so we can plug them in. For the point 0, comma 1, x is 0, so we're getting a 3x squared plus 1 is 1 and 2y, y was 1, so we're going to get 2y is 2, so we get 1 half, but 1 is congruent to 6 modulo 3, so you get 6 over 2 or 3. That means the slope of the line connecting p and 2p is 3, or minus 2p is 3. So if 0, comma 1 is one of the points on this curve, you have to find the second point that is on that contains p and has slope 3, and that turns out to be 4, comma 3. That's actually 7p. Is there an easy way to see that? I said the slope was 3. So if you're going from 0 to 4, 4 is like minus 1, remember? So we're actually, x is decreasing by 1. That means y has to decrease by 3. 1 minus 3 is minus 2, but that's congruent to 3 modulo 5. So that does give you the point 4, comma 3. That is on E. That's 7p. And we have to negate it to get 2p. That's 4, comma 2. So that's just one example of the calculations you have to do to calculate these points. And then you can use the addition law to get things like 3p. Maybe I should just do one more example. How would we get 3p? Well, it's the point connecting minus 3p is the point connecting p and 2p. The line is the point on the line connecting p and 2p that's on E. So p is 0, comma 1, 2p is 4, comma 2. The slope of that line, p is decreasing by 1. X is decreasing by 1, going from p to 2p, and y is increasing by 1. That means the slope is minus 1. So we have to find a third point on the elliptic curve. And the claim here is that 6p less minus 3p is 2, comma 4. Let's see, if x goes from 0 to 2, that means x is increasing by 2. We said the slope was minus 1. That means y has to decrease by 2. And 1 minus 2 is negative 1, which is congruent to 4 modulo 5. So that would give you the point 2, comma 4, which is 6p. But now we have to negate it to get 3p, and that's 2, comma 1. So those are just two of the calculations you have to do, and there's not too much other work. I mean, I actually did these calculations myself. I didn't use a computer to calculate any of these points. And you get everything. You get all 9 points, including the point at infinity. So anyway, that's the proof. That's the proof that P generates this elliptic curve E5, and we've even found explicit formulas for every multiple of P. Each one is a unique point on E5. 5. So anyway, that completes this problem. I realize this is a pretty technical problem. You have to know something about elliptic curves and their group law, but once you know that, you can do a lot of fun stuff with elliptic curves. And this is actually a pretty simple example involving elliptic curves. I've done problems involving elliptic curves that are much harder than this one. So anyway, just a little overview about elliptic curves, which is a very important area of math, by the way. A lot of important applications of elliptic curves, including cryptography, and a lot of other stuff. So anyway, that completes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.